Welcome back to Guide, and our focus for the last few lectures has been the sorting algorithms, and today the focus continues, and we'll discuss a very interesting sorting algorithm called heap sort. Okay. This is a very interesting algorithm, and it has some nice properties. It's a comparison-based algorithm, so let's write out the bullet points. Okay, this is still a comparison-based algorithm. That means it's similar to merge sort, quick sort, and all those very well-known algorithms. Okay, and it's a part of the selection sort family. Okay. Another nice property is it's an in-place sorting algorithms. Okay, not all algorithms, all sorting algorithms are in place. However, it's not a stable sort. That means two items being with the same key may not maintain the same position or same relative positions at the duration of the sorting. So not a stable sort. Okay. So before we go and discuss what heap sorts is, we need to first find out what is a heap. What is heap? Okay. This is not a heap of memory that you typically hear. So this is heap with a certain property. So heap is a data structure. So you can have a max heap or a min heap. Okay. And these two are changeable dual concepts. So we'll just focus on the max heap. So what is a max heap? Max heap has this nice property. So it's a tree structure. It's tree structure. And let's just focus on binary heaps. Okay, that could be ternary or even based on how many branches you have, you could be having. Okay, so binary heaps, just focus on those. And what is the property? Property is the parent is always greater than equal to the child in terms of value. Okay, now let's just look at some example. Okay, so suppose we create a heap. So the parent needs to be greater than the child. So 30, 40 maybe. And again, for the subtree that is rooted here, it has to have that property. Subtree that is rooted here have to have this property. It could be 25, it could be 35. Okay, so this is a very nice property. And the property is the children and the parent should satisfy this less than equal to this thing. Similarly here, it's less than equal to. Now you see 35 is actually greater than 30 because the relationship does not guarantee this. So this is not a binary search tree, this is just a heap. Now maximum is the root, and that's what the heap sort uses. What it does, it creates a heap based on your current data set and then extracts the root that is always supposed to be the max of the remainder of the data set, and then it rebuilds it. So delete the root and then rebuild it to guarantee the operation. Okay, so the rebuilding would be fairly similar. So how will you do that? Say, now suppose you delete this guy. Okay, if you want to delete this guy, then what happens is, here I'll illustrate in a small space. Look at the bigger one of these two, and that should be promoted as the root. So this becomes the root now. Okay, and then one half of this stays the same because it's still smaller, and the bigger of these two becomes the right child. and automatically this become a child of the child, and this maintains its property. So this is a delete root operation. So the way the heap sort work at a high level is, first is build heap from the unsorted part of the array. Okay, then delete root to get the max, and then rebuild heap. That's it. Heap for the remainder. So that's what it's doing, is building the heap, getting the max, deleting that thing, placing the max into the right correct order in the final array, then again rebuilding. And rebuilding is just delete root. So after delete root, just massage the tree so that it again becomes a heap. So the complexity of this algorithm is, worst case is log n, and best case obviously is order of n log n, but it can be shown to be omega of n. Average is again order of n log n, and space complexity, there is an in place sorting, because the heap, you are maintaining the heap by manipulating the pointer, so you are not actually copying the remainder of the array and building a heap in its separate data structure. You are actually keeping the heap and using the heap, using the array elements. So you're just introducing pointers, and then the pointers are actually pointing to the actual data that is the unsorted part of the array. So that's why it is an in-place sorting, and that's one of the key advantages of heap sort compared with quicksort and merge sort. It can be shown that in more well implemented quicksort will outperform heap sort, but if you need in-place sorting, then this is the way to go. Plus order of constant for the pointers. Okay, so this is a very interesting sorting algorithm, and there are other variations, and we are not going into detail of those things. We'll go into details later on in the subsequent lectures. And one, just the trivia, is the smooth sort. What is a smooth sort? It always shows up at interviews and can catch you off guard. It's a smooth sort. It's a variant of heap sort. It was developed by none other than one of my professors, Edgar Dijkstra. And smooth sort's upper bound is n log n. Advantage is it comes closer to order of n time if the input is already sorted to some degree, whereas heap sort average n log n regardless of the initial sorted state. Okay, so the only thing is if almost sorted, okay, sorted, then smooth sort is around order of n, but heap sort it's still order of n log n. So this is just a piece of trivia. This is rarely used though, because it's so much dependent on the type of the data set and the complexity involved. So okay, I hope you enjoyed it. We'll get back to you with more sorting algorithms later. Bye.